Hello, everyone. Amelia Fang in YouTube chat. Hi. Let's go! It's happening. Let's go. Hello. People are really taking their time today. No one's made it in over here on Twitch. Ah! Just kidding. Generics here. Hi, Generic. Wow. Hi, everyone. I hope everyone's having a decent evening so far. Wow. What's everyone been up to today? Seems kind of like people are still drifting in slowly. We'll hang out, give people a moment. I can eat my food, because I just got home. I failed calc in high school. Let's go. Well, the past two Sundays we've met, we've just kind of been reviewing pre-calc material. And so today is kind of the first day that we're really kind of starting like the calculus material. We're going to be getting into limits today. And so really like we've just kind of done the preface and now we're actually doing chapter 1. And so if that sounds interesting to you, and you would like to learn some calculus, well then, you're in the right place. I'm gonna eat this sandwich. Sandwich gaming. I do like this song. Always gets me hyped. Let's see, what should we listen to today for the rest of the stream? Maybe some like Forlung and MetaRoom webcore type stuff. Okay. All right. Where did my thingy go? Where did I put it? Oh, it's right here. Okay, well, let's jump into it then. So today, we're really kind of getting into the meat of potatoes of calculus. And so we're just kind of going to go through chapter 1 here. I like how it kind of lays things out and kind of sets the stage for what we're going to be doing. Math. So, what is calculus? Well, it says calculus is the mathematics of change. And so it's all kind of about like, really kind of like one of the things that gets us in the step, or like a step in the right direction is kind of like thinking about, you know, what are we doing in calculus, is sort of thinking about what happens if you focus on like two parts of like a function or two parts of some sort of system, or even multiple parts, any number of parts really, and you let like those parts change slightly. what kind of happens to the system overall? And that's kind of like the main question. And so kind of what we're going over in this calculus course is really calculus of a single variable. That's kind of like what the book is called, calculus of a single variable. But you can have like calculus. You can have calculus questions or like systems of calculus and that sort of stuff that have any number of kind of like variables that you're letting sort of change with respect to another. Math. Yes, exactly. Twitch chat. We gotta cook. We gotta cook, Twitch chat. And so they've got like a graphic here, which kind of sets the stage a little bit. Maybe it's a little bit of an oversimplification, but at the same time, it's not really. It's not really an oversimplification also, where it's like, you've got pre-calculus mathematics, and then, everything that we've talked about over kind of the last 2 sessions. And we're going to add in this idea of something called the limit, and kind of like the limit process, and sort of like taking the limit of things is what we're going to talk about today. And through that limit process, we're going to be able to develop kind of the key pieces and the key mechanisms of calculus that we're going to go over. And so, it says here, the second stage is the limit process, and the third stage is a new calculus formulation, such as a derivative or an integral. Derivatives and integrals, what are those? And so, yeah, so that's, chapter 1's going to kind of be all about the limits. And so, it's kind of like this idea, it's going to be this kind of like first important thing that we're going to go over. And so, let's see, what are these? What do we got here? Okay, yeah, this is just going to kind of be showing the things that we're going to kind of be doing, or that we're going to be able to talk about with calculus. I got water. I am prepared to hydrate. But yeah, so basically, like, calculus lets us take lots of these things that were maybe like very simple, like, cases, and expand upon them and make them more complicated cases and kind of figure them out, essentially. And so this is kind of one of the first things that we talk about whenever it comes to like calculus. So I guess maybe to set the stage here for like, what are we trying to do with calculus? Like what's the point? What are we getting at? Like, what are we working towards? And so one of the first things that they kind of pose in this book is like this quote-unquote tangent line problem. And so one thing that maybe like to kind of touch on is, like whenever we're talking about like slopes of functions, like if I just come over here and I were to have, some function, some coordinate grid here, and maybe this axis is time, and this axis up here is distance, then there's a relatively straightforward interpretation of kind of like what the slope is. Whereas like if I have some line here, well, the slope, like if we were to go from like this point over to this point, where have you been uploading the VODs? I can't seem to see them in your YouTube channels. So if you go into the mathematics Discord or my Discord and go into the exploratory calculus like thread or like forum post, there's a link to a playlist. There also should be on a playlist on my VODs channel, but you should be able to find them in a playlist. Otherwise, you'll be trying to find them amongst all of my like live broadcasts. But if we were to think about like the slope of this line as kind of like calculating it between these 2 points, well then, this like vertical component over here, like we know slope is rise over run. And that's kind of more mathematically stated as like a change in y over a change in x. But in this particular instance, as of like, what that means in the context of this graph, well, that's some change in distance over some change in time. Awesome. And what is distance over time? You may remember that if you took like basic physics, that velocity is distance over time. And so sometimes there are cases where like, like these quantities that we talk about, like the slope of a line, corresponds to something like directly. And so like in this case, if you find the slope of a line to a function, then basically what you found is its velocity. You found the change in y over the change in x. And so if what we've done is graphed time versus distance, that becomes change in distance over change in time, which, as stated, is velocity. And so from there, we can even, like expand upon that. Like the formula for like acceleration is velocity over time. And so if you had like a graph of, velocity versus time instead, then the slope of that line would be acceleration. And so there are times where we do want to be able to know kind of like what these slopes are, like what the slopes of these functions are. And in this case, it's very easy to figure it out because it's just a straight line. The slope is always the same. But what if we have another function and so what if we had another function where, let's say it's still time versus distance. But in this case, it's not just like a straight line. Maybe it's like a parabola or something like that. And it kind of goes off like this. Well then, how can we find the slope at any of these points? I mean, like, the only way we know how to calculate slopes as of this point is with that kind of like change in y over change in x. And as far as we know up to this point, that requires some value of like y2 minus y1 over x2 minus x1. But if I wanted to know, like, okay, based off this graph, what is the slope just at this point right here, at a singular point? I want to know what the slope is at this point so that I can figure out the distance. Well then that's not as easy of a question anymore because, well, we only have one point. We can't just plug in like 0 for x and y because that would be using like 0, 0 as another point. But that's not true because we don't want the slope going from 0, 0 to our other point. We want the slope like at this instantaneous point. We want the slope that's like tangent to this function. And so it would maybe look something more, I don't know, like this. And it would just kind of go through like this single point and only this point. And it wouldn't go through any other points on the line, at least not immediately around it, not around where we care about. And so how do we figure that out? How do we do that? And that's kind of like the question here, and kind of one of the first things that we kind of seek to figure out in calculus. And that's kind of like one of the big questions. And so, one way that, I guess let's move on now to kind of to limits and kind of investigate, what sort of formal tools might we think about, and what kind of things might we be able to do to help us solve that question. And so importantly here, they give us this formulation for like the slope of a line. More importantly, it's like the slope of a secant line. And so what they kind of show here, in this graph right here, if I were to zoom in, what they're showing us here is that like the slope between these 2 points is like we have some delta x, and so we have like this point here that's at like c comma f of c, where whatever this function is, this point would be at, you know, if we plugged in c for x, then it would be f of c for y, because, you know, the y value is whatever the output of the function is evaluated at that x value. And so then if we were to start here and we were to go over some delta x, well then our new point would be at c plus delta x. And so then we would plug in f of c plus delta x into our function to figure out what our y value is. And so a way that we could write this formula for the secant line in terms of functions is, you know, you might see it kind of sometimes written how they did here, where we could say like m, let's do this just in white, where we could say m is equal to f of c plus delta x minus f of c all over c plus delta x minus c. And so what this effectively is here is like this top here is our delta y, or really it's kind of like our change in our function. And then this bottom value down here is our delta x. And so it's kind of like our change in our x values. And so I'll write that too. Change in x value. And so really kind of what's going on here is like we're starting at c, we're starting at some arbitrary x value, and then we're saying, okay, well basically like if we just go over a little bit, then what happens? And so like we can calculate the secant line between 2 points just by kind of like starting at a point and then going over a little bit on the function. And so I do actually have a Desmos graph that I made for this. Here, let me go open that up really quick. Yay, Desmos! And so what we've got here is I've got this function e of x, and so I can say, okay, let's put, you know, like our starting value wherever, and then we can move this other point, and then we can say, okay, well, like if, you know, this point is over here, then this is the slope between the two of them. And you can kind of see that slope written here specifically, where we have like f of a plus h minus f of a all over h. And that's kind of what we've got here. Except instead of c and delta x, I've used a and h. And we can see here as well that if we kind of like follow through with this, what we've got on like the bottom right here, these c's can cancel out, because we have c and then minus c. And so you could see like the difference quotient written like this, where it would be f of c plus delta x minus f of c and then all over delta x. Or you sometimes see it written slightly differently, where you might have like f of x plus h minus f of x all over h. But these all kind of like stand for the same thing, where, you know, like basically we're saying we're starting at whatever, like some x value, some arbitrary x value, and then we're gonna like move over a little bit on the function by h. And then we're gonna kind of see like what's the slope between those two lines, what's the difference, hence why this is often referred to as the difference quotient. Difference quotient. Hey Obi, how's it going? Are you having a good evening? And so, let me see. And so, what do they talk about next? And so, yeah, and they have a little bit here kind of giving us a hint at kind of what's going to be happening. And we can see it here if we go back to my Desmos graph here. You know, we're interested in kind of figuring out what is like the tangent line for the function. And we can see obviously right now this line is not tangent because it's going through two different points. For something to be tangent, we need it to go through only a single point. However, if I were to bring h, this orange point, down closer and closer to our value of a, then we can see like as they get closer and closer together, the line starts to look more and more tangent. But you can see even still, if I were to like zoom in here, they're not tangent, it's still going through two different points. But as I were to like continue to try and get them closer and closer together, then eventually, in theory, it looks like it's getting more and more tangent. But we have a problem. If this is how we define our slope of our tangent line, well then once h actually has a value of 0, so that our distance between like h and how far we move over is 0, well then we have a problem, because that would mean then we're dividing by 0. And you can see that our secant line now is gone. It's undefined.
What is your thoughts about this third meeting, Exploratory Calcu course? Homework help open. Pride. Commands. D.
I'll be right back.
Help stream.
The joy of students exploring calculus with a mix of desperation and hope. I can almost smell the aroma of confusion from here. Pride, commands, and math help sounds like a fun cocktail of potential chaos. Maybe if they succeed, I'll recruit them for my world domination plans. But remember, never underestimate the power of math in plotting global takeover. And now where's my banana milk and maybe a lobster snack for support?
I'm back. Hey Jay. Also, hi Famished. Everybody's making their way in. Jay, I see what you asked on YouTube. What's today's lesson? Are we proving limits? So that's an interesting question. We are going to be talking about limits and like, you know, limits as like a process. But we're not necessarily going to be going so far as proving limits necessarily. And so usually kind of like the proof for limits is usually something called like the epsilon delta approach to limits. And that's actually something that Penn Center is going to be covering in their real analysis course that they're kind of managing. And so if you make your way over to either the mathematics Discord, or you join Penn Center's server, the Elements, and you kind of get in on their real analysis course that they're covering. The epsilon delta approach to limits is something that they're going to talk about. So yeah. Good to see these widgets are here. Yeah. Yeah. Also, hi Blue. Welcome in. We're doing a calculus course tonight. And so, you know, Monday through Saturday I play games. But
Quipaglius squiguaglius.
Quipaglius. So Monday through Saturday we play games, but Sunday we're doing math. And I plan on going back to school in the summer, and so there's probably going to be more math streams then, just because I have homework to do and talk about. But yeah. And so today we're continuing our calculus course, and we are starting to touch on limits. What are you going to school for? I'm just going to be... So I actually I've already gone to a lot of school, and I was originally getting a degree in electrical engineering, and I got like 85% or like 89% or something of like all of the credits that I needed for my electrical engineering degree. And then I just like couldn't get any further because like my heart just wasn't in it. I was just like, you know, like I was just doing it for the wrong reasons. Like I had much more of an interest and a love for like all the theoretical stuff related to it. And I've been teaching for a long time. It's okay. The professors for EE were ass. I mean, I wasn't gonna call them out like that, but yeah, it was a hard time. And it didn't help that like a lot of my earlier electrical engineering classes that happened were like online bullshit classes that happened in the middle of like COVID. But I've been doing teaching and teaching tangentially, like teaching related things for a long time. And I seem to have a real talent for teaching, and I enjoy teaching. And so I figured, how about I just get a degree in math and, you know, do what I find that I'm good at and that I find fulfilling, which is probably teach. And so that's my plan at the moment. But I already have like 70, because of what I had done for my engineering degree. I already have a minor in engineering physics, and I already have like 70-something% of like the mathematics credits that I need to graduate. I just have to do it. I just have to do it. 8+ years, actually. I did some bad math. Yeah, I've known you since high school, and so that would have been that year, because you did that 1 year, or I started, but then you started in that order, and then yeah, I mean it's closer to like 9 or 10 years, yeah. Because we would have met in probably like 2015, like second half of 2015. How old are you, Talos? I am. My age is undisclosed, but I am in my mid-20s. I'll say that much. Older than the sun. I mean, when was Talos built by Hephaestus? What year was that? Third century BCE. You know, at this point when you're that old, the years just kind of fly by. I know Dawn is like 7 years older than me. I don't know how old Dawn is. Dawn doesn't seem that old to me. I wouldn't be surprised if he was older than I am, though. Wait, are you saying Dawn is 7 years older than you or 7 years younger than you? Seven years older than me. I mean, if Dawn is, you know, teaching math on the internet and he's having a great time, then I don't know, that should be like refreshing to you in a way. Like if, you know, 7 years from now you're also like on the math or like on the internet teaching math or whatever, then like you've got plenty of time. No need to be in a rush or anything. But yeah, math. So yeah, so we got this kind of like visualization. So what I had just mentioned is, you know, we have like a way that we can kind of define how to like calculate the slope of a function. Where we can say that like the slope of a function, we know it's like some change in y, like a rise over run, some change in y over change in x. And usually we calculate it with like 2 points, like a y1 and a y2, and an x1 and an x2. And we can kind of describe that y1, y2, x1, x2 using like function notation. And so the way that they kind of describe it in the book is with this formula here, where basically like what they're saying is if we start at some point c comma f of c, where, you know, if c is our x value, then we plug that x value into our function to get our y value as our output. And so one of our points would be c comma f of c. And then we can basically say, okay, what if we go over a little bit, some delta x? And so if we go over delta x from c, then our new point will be at c plus delta x, comma, f of c plus delta x. And so our new x value is c plus delta x, then basically we're adding, like that's what we're plugging into our function now. Here, what if I do actually highlight these? And so these are like what our new points are going to be. And so that's where we get like this formula here. And so we have f of c plus delta x, that's like our y1, minus f of c, that would be like our y2. And then we have c plus delta x is our x1, and then c would be our x2. But c and then minus c, like shown here, just cancel out and give us delta x. And so that's kind of where we get this work here too. And so you can see I wrote up here, this is our delta y, on bottom we have our delta x, and so we get this formula here. There is another way that this formula is kind of often written that you usually kind of see in books and things like that, where instead of f of c plus delta x, sometimes they'll write it like this, where it's f of x plus h minus f of x all over h. That's at least how it was introduced to me. Where, you know, it was basically still saying the same thing, where, you know, we're saying we start at some arbitrary x value, and then if we go over a little bit from that x value, go over some amount that we call h, then we can calculate the secant line, like the slope of the secant line, using this formula here, using this what we call the difference quotient. And so that's what I was showing here with this Desmos graph. And so then what we can say is, you know, if we have some value a that we plug into our function, some arbitrary x value that we start at, then we can drag this point around here. If I make this something more like, x squared, for instance, then we can see if I go like from here to here, okay, well, this is a secant line between the two of these, but it's definitely not like a tangent line. It goes through 2 points. It doesn't even look like it's tangent to the graph. But if I were to bring these points like closer together, well, then maybe it's like getting a little bit more believable that it's closer to tangent. I mean, here you can still obviously see the gap. And so it's like, well, yep, this is definitely not a tangent line or anything like that. But the idea is, as we get closer and closer, as we bring H closer and closer to A, then it looks more and more like a tangent line. Like if we were to just like zoom out kind of far and just like look at this and kind of squint our eyes a little bit, like that looks like a tangent line to me. And I think it would look like a tangent line to most people. But it's not until we zoom in really far that we can see, okay, well, it's still a secant line. It's still going through 2 points. And that much is just evident by the fact that we know it's going through this point and this point. But as we bring H closer and closer to A, that approximation gets better and better. But we do have a problem with like, okay, well, why don't we just make H and A the same value? Or like make, if H is the distance from A, well then we need H to be 0. But if H is 0, then that means that this part of our function right here, that gives us our slope, kind of gives us our delta x on bottom, is 0. And so we would be dividing by 0, and that's a problem. Because if we divide by 0, then it's not going to be defined anymore. This material is so derivative. Boo! Boo! Bring better math jokes. But do bring more math jokes. We do need more. And so that's kind of like our problem here. Like we have this idea where if we could get A and H closer and closer together, then we get closer and closer to a tangent line, but we can't just have H go, like we can't just let H be 0 because then we're dividing by 0. And so that's kind of like our problem here. So like maybe we're on the right track, but we don't quite have all the tools that we need to solve this problem yet. And then we also have like the area problem that we'll get back to kind of another time. And so I'm just gonna kind of gloss over that for this moment. And so the idea of kind of like a limit, and in its like the spirit of the idea of the limit, Ultimate Doom says, there is a small sidetrack here. Next to the forward difference, there's also the backwards difference where F minus delta is used, and the central difference where plus and minus are used. I don't know that I've ever seen that. But I guess it would kind of be like similar, where it's like you're using some value to define where 2 points are and then calculating the slope between those 2 points. Where you're just kind of like treating F as like a midpoint, or like your initial X value as like a midpoint, essentially. It becomes relevant when considering Monte Carlo derivation techniques. Great. I've been using comma a lot for a decimal lately. Do they do that in the UK? Are you still over in the UK, Obi? So they've given us a graph here, something to consider, where we have the graph of x cubed minus 1 over x minus 1. And so one thing that they, show here is that this function has like a hole in it. It has what we call like a removable discontinuity, where if I were to just graph this here, x cubed minus 1 over x minus 1. Let's see, turn off our points for now. And so this graph, it's got all these points. It's a classic parabola. But right here, where x is equal to 1, what, 1 minus x? Oh, because I'm at x equals 0. That's my problem. Losing my mind. Okay, yeah, here when x is equal to 1, there's a hole in the graph. And so right here where x is equal to 1, you can see it says that it's undefined. And so here, if I were to put a line here, so x equals 1, then where these two functions meet, there will be a hole. And see, it doesn't even want to like show them meeting, because technically the function's not defined here. And so, but like, for us, just kind of like looking at this function, it looks like it goes through 1. Like if it just weren't for that removable, like if it weren't for this denominator here, making it x minus 1, like we could go through this function. And if I were to like expand this out, and so if we had x cubed minus 1, x cubed minus 1 over x minus 1, and I were to use the sum and difference, or like the sum and difference of cubes for this, then this would be, what, if I remember correctly, is it the first is the same and the second's different? So like x minus 1 times x squared plus x times 1, which is just x, and then plus 1 squared, which is just 1, all over x minus 1. And so then the x minus 1 on top and bottom would cancel. And so we would just be left with x squared plus x plus 1, which if I were to plug that into our function, then these look exactly the same. They look like they overlap each other entirely, except for this one is defined at x equals 1. And so we've got 1 comma 3, but on this one, that's a hole, so it's undefined. And so there's kind of like this idea here where it's like, okay, well these functions are like really close to being the same, and like graphically, they might look exactly the same, except this one's got a hole at -1. Or I'm sorry, this one's got a hole at x equals 1. And so the idea here for like, I too have a hole where my x used to be. That's okay. That hole is simply a removable discontinuity and can be ignored for the most part. Or you can talk to your therapist about it. And so the idea here with limits is, what if we kind of like ask ourselves about this idea of like, what happens to the function as we approach a value? And so if we're like kind of getting closer and closer to a value, then what does it look like the value approaches? There is like a touch of hand waving here, because, as we're just kind of talking about this with limits, this idea of kind of like, what does it mean to approach some value isn't defined rigorously necessarily, but it's something that can make intuitive enough sense when you kind of like approach it this way, where like for this particular function, we can see as like shown in this table here, I was always confused about how rigorous it is. And so it's something that I mentioned earlier, but it is actually something that Penn Center will be kind of going over in their real analysis course that they're managing. And so if you either find yourself on the mathematics Discord or on Penn Center's server or in the Simple group or anything like that, you will be able to find resources that kind of touch on what has been come to known as like the epsilon delta definition of a limit, that kind of like more mathematically defines what it means to like get close enough to a value to actually say that like, okay, this limit is equal to this number. That's kind of like the problem here. Like, how do we know that as x gets closer and closer to 1, that this function is getting closer and closer to 3? It might actually be getting closer and closer to 3.0000000001. But how do you prove it's actually getting closer to 3 and not 3 with a long string of zeros and then a 1 on the end? And so there is a teeny tiny touch of, glossing over that we are going to do here, just because it's outside of the scope of kind of like what's typically covered in a normal introduction to calculus, and requires some analytical approaches that, we haven't necessarily talked about here. But I encourage you to go to the mathematics Discord or go to, wherever to find the resources to learn about that if you're curious. Absolutely. But, kind of as we talked about, for this particular function with the x cubed minus 1 over x minus 1, if we were to kind of divide out this denominator and cancel with what it has on top, then it would just be like the same as this function, which looks like it goes through 3 no problem. Let's see, the math help command has a link to the mathematics Discord. For this function, you can prove that there's an x closer to 1, where f of x is closer to 3 than any number other than 3. Yeah, I mean, you're on the right track. Trying to do things numerically is insufficient. You assume things are nice because students at this point haven't seen things that aren't nice. But yeah, weird things could be happening. But polynomial functions are continuous, and they approach the value you get from just plugging in. Yep. Yeah, and so kind of the idea here, at least kind of what we're going to kind of follow, at least to kind of figure out this question, if we were to just look at it numerically, then we can see as x gets closer and closer to 1 from either side, so as x approaches 1 from the left or as x approaches 1 from the right, then it looks as though f of x, its value, if we were just plugging these things into the function, is getting closer and closer to 3. And if I wanted to like go into my calculator and actually say, okay, well, what if I plugged, x like is 0.99999 into this? And so if it was 0.99999 to the power of 3, all minus 1, and then divide that by 0.99999. Uh-oh. It's going to divide by 0 here. Or it's going to be 0 divided by that. It's this. And then divided by 0.99999 minus 1. Then we get something that's even closer to 3. Blah! Where was it? It should have been there. I have had problems, some people have had problems with the redeems updating dynamically. I don't know, if you were looking for it and it wasn't there, I could test it. What value? What are you asking about, Obi? Captain of the Argo, or not that one? Nah, it's like a separate surprise VIP one. If I test it. Did it open? I thought I tested it. It's supposed to be like one channel point, so it would open at the top. Let me see. Well, I just enabled it again, and so it'll happen again randomly somewhere between 10 minutes and 2 hours from now. We were talking about like a channel point redemption. So I'm Talos from the Greek mythology of the Argonauts, and yeah, that's why there's like an Argonauts theme here. What happens when it's discontinuous? What about step functions? The limit as x goes to 0 of sine of x. So there's two important parts about a limit. And so it's kind of, you know, what we're getting at here. And so they talk about here that, you know, they mention for this function that x approaches 1 from the left, and as x approaches 1 from the right, then both sides seem to approach 3. And so it's really important here that whenever we just talk about like a limit generically, then we usually refer to that limit as just like, you know, kind of referring to both sides. But one of the kind of first kind of contradictions to that we come across would be something like, let's see if we can scroll down and find it. Yeah, they go over it right here. And so limits that fail to exist are limits where basically like if as you approach from the left or as you approach from the right, if they disagree, then we would say the limit at that value does not exist. The limit from the left might exist and the limit from the right might exist, but the limit kind of spoken generically referring to the limit from the left and the right together disagree, therefore those values, like that particular limit would not exist. And so like here they have show the limit as x approaches 0 of the absolute value of x over x does not exist. And I had never actually considered that the absolute value of x over x is a step function. That's interesting. Monte Carlo methods help approximate the derivative even when there are such discontinuities. It's not actually something that I know anything about, but the whole idea of like Ito calculus was super fascinating to me, where like the entire methods are for like stochastic processes that are like infinitely non-differentiable. Blows my mind. But that's not here or there. And so like the whole idea is that like if we were to look at the function, so it's like the classic argument of dividing by 0. Not exactly. I mean, there is part of the problem where if we were to say like if we actually let x go to 0, then we would be dividing by 0 here for this function. And so maybe this exact like function doesn't exactly work, but you know, we would have been dividing by 0 up here too. And so like if we were to say what's the limit of this function as x approaches 1, well then if you actually just plug 1 into this, then it breaks, because you would get 1 minus 1 over 1 minus 1, and that would be 0 divided by 0. And it's kind of like, well, what the heck? We're dividing by 0, or, you know, as a matter of fact, 0 divided by 0 is actually what we call like an indeterminate form, so who knows what the heck it's doing. But the whole idea is when we're talking about limits, we don't necessarily care like what the value actually is at that point. What we care more about is what the function is approaching as we get closer and closer to that point. And so as we look at this example down here with the step function, where it goes from -1 and jumps instantly up to +1, then if we were to like zoom in here and like look at this function as it were approaching from the right, then as we come from the right, well, then you can see it's like the function, it's constant at 1. And so the limit as x approaches 0 from the right side would be +1, but the limit as x approaches 0 from the left side would be -1, because it seems like as we come from the left side, the function is going to stay -1 as we get closer and closer to 0. Whereas as we come from the right side, it's like it's going to stay as +1 as we get closer and closer to 0. And so the intuition is that the limit from the right will be 1, and the limit from the left will be -1. But the problem is that those aren't equal to each other. And so it's not that like dividing by 0 is the problem, it's that the fact that they disagree is the problem. Yeah, it's like dividing by 0 in that it's undefined. Well, is it undefined, or is it that it does not exist? Because those are subtly different. And so let's look at this other one here. Here, maybe we should just look at like another classic example for like finding limits. And so like here we have another function where if we were to plug in x equals 0, then we would get this value where it's undefined. But if it weren't for this value that's undefined, it would go through 2. And so it's like you can see as x approaches 0 from the left and as x approaches 0 from the right, as we plug in values that are closer and closer to 0, the function approaches 2, is what we would say. And so we would say that the limit of as x approaches 0 of x over the square root of x plus 1 minus 1 approaches 2. And so that limit would be equal to 2. And then like same thing for this function. There's a hole at x equals 2. Or it's not, rather there's a hole in this line at x equals 2, but the value is still defined at that point. And so in this case, you know, as we take the limit of as x approaches 2 of this function, then it's going to care about the line more than the point. And so basically we're saying like, okay, like as we approach from the left side here, then it's constant at 1. And as we approach from the right side, it's still constant as at 1. It's not until we actually get to x equals 2 that there's this jump in value. But like I mentioned, we don't really care what the function is equal to at that point. We care about like how is the function approaching that point, and using that like approach to determine our value. And so the limit cares more about like the approach, like how we approach a value, rather than like what is the actual value at that point. And so here's like another instance of basically like a limit that wouldn't exist. And so here it says, consider the graph of the function 1 over x squared. And so as we approach from the right and as we approach from the left, as we get closer and closer to 0, it looks like both of these functions are shooting off towards infinity. And so in this particular instance, it says, in figure 1.9, you can see that as x approaches 0 from either left or right, f of x increases without bound. That means that by choosing x is close enough to 0, you can force f of x to be as large as you want. And so, and then let's see. And so then it says, since f of x does not become arbitrarily close to a single number L as x approaches 0, you can conclude that the limit does not exist. And so, yeah, so in this case, we would say that like the limit does not exist because it keeps like basically both sides are approaching infinity. Another term that might come up for this later is it's like the value is diverging. And so in some instances, I feel like you could argue that you could just say that the limit is equal to infinity. But infinity is almost not like a real answer in some instances. Because infinity technically doesn't have like an actual value. It's just kind of more like a concept. It's trying to think of a situation IRL where a step function has a real application. The closest example in my line of work is a failure mode. I don't need to know the exact value when a structure fails. I need to know what it approaches and change the design to fail at a value it should not reach in normal use. Yeah, or the first thing that I think of when I think of like what's a step function in real life is like a square wave. Where, you know, or like hitting a switch in like electronics. You know, something goes from being like 0 to having whatever value it has when you flip the switch on. Or, you know, it's like you could have something graduated tax rates, they round to whole dollars usually. Yeah. Okay. Yeah, you need to know what it approaches. And so it's like, you know that whatever value it fails at, it will have failed. And so maybe like the stress or strain on it at that point would be like 0. But you don't need to know like what the value it is that it fails. You need to know like what stress and strain it's under right before it fails. And so you need to know like what the limit of the value is as it's approaching its failure point. So yeah, that's a good analogy. I appreciate that. So here's another one. This oscillating behavior. And so this could actually be a fun one to plug into Desmos here. If I have the sine of 1 over x. And so it has this oscillating behavior, which is really fun, where basically as x gets smaller and smaller, we're making the period of sine smaller and smaller as well. And so it's like it oscillates faster and faster. And so as we like zoom in, you can see that there's like more and more layers and it just continues oscillating. But like it doesn't really like, if no matter how close we get to 0, it will just continually oscillate like faster and faster and faster. And so if I just tried to like zoom in straight on in at 0 here, then like we would never be able to tell. Like it's so fast that even as I like zoom all the way in, it's just like it looks broken. And so in this case, this is kind of like the classic example of like what happens if you turn.
Talos is a math wizard and you're all math wizards here, so it's a question somehow. Yes, I'm aware it takes huge effort and lots of time to get there. To be a math wizard, tons of effort, respected effort.
Yes.
Oh yes, Talos being a math wizard and all. I mean, isn't it magical how solving equations feels a lot like casting spells? With enough effort, you too can become a respected wizard in the mystical realm of math. Maybe then you can assist me in retrieving my evil plans from the towering fridge. Until then, let's focus on practicing math. World domination comes later. Yep.
Yep. That's right. With enough practice, even you, too, can become a math wizard. Or just a respected wizard in the mystical realm of math. You know what? Forget it. You can choose your own domain, your own mystical realm to become a respected wizard in. But yeah, so this is kind of like the classic example where like you could almost think of it like as x approaches 0, like a idea of kind of like what this could represent would be like, imagine turning like a light switch on and off, but you like as you get closer and closer to 0, you're essentially like turning it off and on infinitely fast. Like the faster and faster it flips on and off, it keeps increasing. And so we like don't know whether it's going to like approach 0 or approach 1 or approach whatever value as x gets smaller and smaller, just because like it's happening too fast. There's no way for us to like squish it down to a single value. There is another kind of idea here though that we could explore. How would I write this? Trying to think of like a good classic like squeeze theorem problem. Where if I made this like x squared, then the further out we go, it starts to oscillate further and or faster and faster. But if I multiply this in by 1 over x, and I'll just scale this all to make it clear, then you can see that like it's oscillating faster and faster. Here, what if I make this even more, like to the power of 4? So it's oscillating faster and faster, but because it's multiplied by 1 over x, its maximum value is always going to be kind of bounded by this line of like 1 over x. In this case, it's technically like 8 over x. And so here it's like we're actually saying that like this is often called like the squeeze theorem, where we're saying that like this function is being like squeezed by these other functions. And so even though this one has a behavior where it's oscillating faster and faster, because it's bounded by this other function, then we can just think about what happens to this other function. And so this is what's referred to often as like the squeeze theorem. But yeah, let's keep going. And so in this case, what does the book say? Because this function has no limit at any real number c, it is not continuous at any real number c. Oh. Is that referring to this question? No, okay, so up here it says for this function, you know, we know sine oscillates between +1 and -1. And so as x gets closer and closer to 0, it keeps going up and down after like infinitely fast between 1 and -1 and never stops or approaches any particular value. Named after famous mystical math wizard Squee. Yeah, it's Squee's theorem. That's right. Squee is a classic kobold name, that's true. Another kobold math wizard, such as myself. And so it says, in this case, the limit does not exist because no matter how small you choose delta to be, so no matter how close you get to 0, it is possible to choose x1 and x2 within delta, delta units of 0, such that it could be any value between 1 and -1. Goblin, actually. I mean, it's true. Goblins and kobolds are like very similar, you know? Where it's like, I feel like goblins are kind of like, what if you made like an orc into a raccoon? And like kobolds are like if you made like a dragon into a raccoon. We're just kind of like the raccoon versions of slightly larger creatures. And so it says here, common types of behavior associated with non-existence of limits. What are raccoons the raccoon version of? Bears? I would say. Like, raccoons are like the raccoon version of bears, maybe? Hi Zev. Who remembers Weatherlight? I'm not sure what Weatherlight is. Or I guess, I mean, I know of a few things that are called Weatherlight, but I guess it's like, what are you referring to exactly? And so, common types of behavior associated with non-existence of a limit. So we've got f of x approaches a different number from the right side of c than it approaches from the left side. And so this would be like the step function that we talked about. And so for a step function, from one side it approaches like a negative value, and from the right side it approaches the positive value. Yeah, I know. How does f of x equals sine of 1 over x times 1 over x play out? You talking about like this squeeze problem that I had here? And so ignore these like artifacts here. This is just from how Desmos renders it. Or 1 over x times 1 over x. Oh. That's an interesting question. I mean, so we still have this oscillating behavior, but now this oscillating behavior is like, it seems to be unbounded, but if I recall correctly, maybe this one does actually have a value. I don't remember. I think that there is like or no, it's like sine of x over x. Or I can't remember. Yeah, so it is this one, where it's if you have like the sine of x over x, it approaches 0. Or it's like, it's undefined, but its limit approaches 1. But if this were 1 over x inside, then I feel like you have the same sort of problem where it's oscillating infinitely fast, and it is now, instead of being bounded between 1 and -1 oscillating infinitely fast, it's now entirely unbounded. And so I'm sure that as you zoom in further and further, within any distance of delta, you can find values nearing positive infinity and negative infinity. I am realizing my life is kind of unpredictable. I'm watching an anthropomorphic robot explain math while I'm eating shawarma from the back of a place called the Selfie Museum. So, a true example of a step function is as my life approaches anyone else's life, they are never equal at their limits. And isn't that just beautiful? It doesn't matter who you are. Yeah, I'm technically a cyborg. That is technically true. Whoa!
The _Zevran gifted a tier 1 sub to Darius _Dreadmore. They have given 84 gift subs in the channel.
Thank you, Zev. 84 gift subs? Damn. But being a cyborg does mean that I'm at least part robot. Sine of 1 over x times x does, however, converge to 0. Yes, so that's another excellent example of the squeeze theorem. And so if I were to just graph x here, then in this case, this is another instance of the squeeze theorem. Does not have a limit when x approaches 0 because it oscillates with increasing magnitude. Yeah. And so not only is it oscillate with increasing magnitude, but its values are entirely unbounded. You know, it's kind of like a combination of the two problems we had before. the function of ooh woo. So this is actually like another case of the squeeze theorem that we talked about. So this is a good question, Ghost Avian, where in this case, sine of 1 over x normally oscillates infinitely fast. But if we multiply it by x, then now you can kind of see here, if I graph these lines of x and negative x, then in this case, sine of 1 over x times x is actually bounded between these two linear functions. It's bounded between x and negative x. And so it doesn't matter that this function oscillates infinitely fast as we approach 0. Because it's multiplied by x, as we approach 0, it's getting squeezed down to the value of the linear function. And so as x approaches 0, it will equal 0. That limit will be 0. And so the limit as of this function as it approaches 0 will also be 0. It gets squeezed. And so that's another excellent question. And so it is still, sine of x is still, a sine function though, where technically its value is bounded between 1 and negative 1. Actually, does it approach 1 asymptotically here, or does it cross 1? That's interesting. Honestly, I don't actually know why this function would be asymptotic. Because without... I guess it's because it's getting closer and closer to 0. And then x is increasing, that they're increasing at nearly the same rate. So it moves faster over a small distance until it is basically moving infinitely fast and completely still. My brain. Yeah, so we're talking about limits, Zev. And so now we're kind of getting to this kind of initial idea in calculus where it's like, we're talking about what happens as we approach a value, as opposed to like, rather than asking about like, what is the value equal to, we're more so asking like, what does the value approach? And so like another kind of like, to use the same example that we went at before, if we have something like x cubed minus 1 all over x minus 1, then this function, it looks totally normal, but whenever x is equal to 1, you can see it says it's undefined. Because if we plug 1 into this function up here, 1 cubed is 1, minus 1 will be 0, and then we divide by 1 minus 1, which is 0 again, and so we divide by 0. And so that's broken. It's not defined. You can't divide by 0. But we can talk about what is the function approaching as we get closer and closer to that value. And so if we kind of like look at kind of what they mention here, as we approach 1 from the left, or as we approach 1 from the right in terms of our x values, then the values of our function, you can see here it goes from 2.3 up to 2.7 to 2.9 to 2.997. And if you plug like closer and closer values in, which we did do that before with like x equals 0.99999, then you get like 2.99997, and so it's getting closer and closer to this function. Or it's getting closer and closer to 3. And yeah, and Yeet brings up like holes, and we did actually go through like, if you took this function and you expanded it out, this is actually a removable discontinuity. That's usually how holes crop up in functions. Where if we actually divide that hole out, or basically like divide out the portion of the function that's causing the hole, you get x squared plus x plus 1. which looks exactly the same. They look like exactly the same function. If I toggle these on and off, you can see they are completely on top of each other. The only difference is this one does not have a hole at x equals 1. And this just kind of like further strengthens the intuition that as x were to approach 1, basically like the value of this function approaches 3. Sometimes it's, you know, not so easy to tell kind of like what the value of the function will approach. And that's kind of what we've been talking about. But this kind of like idea of, instead of like, you don't care what the function like actually is equal to at that point. Like we don't look like when we're talking about the limit as x approaches 1 of this function, we don't necessarily care that this function is undefined at this point. We don't care that it's undefined at 1. All we care about is how this function is approaching like a particular y value as we approach 1 from either the left side or the right side. That's the entire idea of the limit. What the function? And so, let's keep going. So yeah, so these behaviors, they said as f of x approaches a different number from the left side, or from the right side as it approaches from the left side, that's when the limit doesn't exist. And so that was like the step function up here. As we approach it from the right, it's equal to 1, but as we approach from the left, it's equal to -1. So this limit does not exist. F of x increases or decreases without bound as x approaches c. And so that was like this one here, where from the left and from the right, they were both increasing towards positive infinity, unbounded. And so as you get closer and closer to 0, you could make your value arbitrarily large. This is making my brain hurt a little bit. I'm gonna dip out, have a fun mathing. Thank you, Zev. I wish you the best of luck. Or if f of x oscillates between two fixed values as x approaches c. And so this is an interesting definition here, because like if we kind of go back to what we talked about earlier with sine of 1 over x times 1 over x, then these values aren't fixed. It's not oscillating between two fixed values. It's like oscillating between like unbounded values, where like as we get closer and closer to 0, it's oscillating infinitely fast, but the values that it's oscillating between are getting larger and larger. Like you can see there's a peak of a value here. And then if you were to zoom out, you could find more peaks. And so it's like the peaks are getting larger. And so it's like, it's a combination of the problems of like the values being unbounded and oscillating infinitely fast. You get 2 problems for the price of 1. That's me if you were to, you know, buy me from a TV ad. Call now and you get 2 problems for the price of 1. There are many other interesting functions that have unusual limit behavior. And an often cited one is the Dirichlet function, where it's 0 if x is rational and 1 if x is irrational. Whoa. That's a crazy idea. Because there's like a countably infinite number of rational numbers. But there's like an uncountably infinite number of irrational numbers. Isn't that the case? Clay. Clay. Must be French. Oh, he's German. Doesn't that mean some infinities are bigger than others? Yes, there are. The name is probably French, but he himself is German, I guess. Q is countable, R is not. Uncountably infinite rationals and less countably infinite irrationals. I think it's the other way around. So the R, like the rational numbers, are countably infinite. I thought infinity was irrational. How can some be bigger? So this is a fun question. And so the kind of simple idea here, hi Pen, the simple idea here to kind of think about or grasp why some infinities could be bigger than others. And so this is just kind of like a surface level thought process. Imagine we have two number lines. And so on one number line, you know, we just have like the whole numbers. And so we have 1, and then we have 2, and 3, and 4, and so on. And then 5, and then 6, 7, 8, 9. Oh, I wrote 8 again. I'm a math wizard. 9, 10, 11, and so on. You know, we have infinitely many just like whole numbers, just counting numbers. You go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on. There's an infinite number of them. But like you can very cleanly define a process to go through all of them. But if we just imagine all of the real numbers between say like 0 and 1, well, we could say, okay, well, we've got 0.1 and 0.2 and 0.3 and so on. But oh, we can also go between 0 and 0.1 and say, okay, well, we've got 0.01 and then 0.001. And like, if you only wanted to give the real numbers that were constructed of like 0 and 01, then like you could assign every single one of these numbers to like a real, like a counting number. And then at some point, I mean, really, you maybe would want to think about going like the other way, but at some point, you could like hypothetically like get through all of the counting numbers and still have infinitely many more real numbers to go through. And so it's like you can define a process to go through all of the whole numbers, but if you were to define that same process for the real numbers, then you, like if you were to use that same process on the real numbers, you wouldn't be able to define all of them. The number of zeros between the decimal and the second number in the sequence is a countable infinity in and of itself. I don't know if that's a true statement, but I think you've got the spirit of the idea. And when I say I don't know if that's a true statement, I legitimately don't know. Some people called Cantor a corrupter of youth for insisting that there are different infinities. I love corrupting the youth with knowledge. The Weierstrass function. Should we take a look at it? Well, you can count each zero, but you can keep adding zeros. Maybe. I'm not saying you're wrong. I'm just saying that, like, perhaps I am not fully convinced yet. I have a complete list of reals proof. I mean, I've usually seen it kind of like in the idea of like, if on like one axis you had the whole numbers and on the other axis you had like the real numbers, then like you could put a point, like you could have a point at every whole number corresponding to a real value, like a real number value. But it's like at some point, like hypothetically, you could imagine, like, I don't know. I feel like I'm gonna say something wrong, kind of by finishing this sentence, but like, it's like you can almost like imagine, like, if you could somehow rearrange, like, get to the end of it. You could assign some, but not every real number. You could do that for the zeros in 0.00 dot dot dot. See, but the problem is hypothetically, in the real numbers, 0.0 followed by an infinite string of zeros, and then at the end of that infinitely many zeros, there's a 1. Technically, it isn't like a number that exists. Like in the real numbers. The real numbers don't have an infinitesimal number. And so you can't have like, you can't have a number with an infinite number of zeros followed by a 1. But you can create a number with an arbitrarily large number of zeros between the decimal point and the 1. There is a number system where that does exist, though, and it's called the hyperreals. And I'm familiar. I know that they exist, but I'm not terribly familiar with the hyperreals. If you have a list of reals, even an infinite list, you can still always find a real number between two reals on your list. Yeah. Yeah, I guess that's a good way to kind of think about it. If you were to kind of like think of the whole numbers and like pick two random whole numbers, then you could continually like get those whole numbers like closer and closer together to each other. Like you can imagine, you know, if we started at like 1 and 11, then it's like we could hone in on like the whole numbers, where we could go like from 1 to 4, and then from like 11 to 7, and then from like 4 to 5, and then 7 to 6. And then there would be like no other, like there's not a whole number between 1 and 6. Or like there's not a whole number between 5 and 6 anymore. Whereas with like the real numbers, you can zoom in arbitrarily far and still like find real numbers between real numbers. I guess that's one way you can think about it. The calculus magnifying glass. Yeah. The Weierstrass function is fun because it's well defined and continuous everywhere, but it doesn't have a derivative anywhere. Yeah, so it's kind of like it's overturning several proofs that relied on geometric intuition and vague definitions of smoothness. Yeah. I love fractals. It's kind of like one of the things that I like mentioned earlier, where it's like you know, like Ito calculus is like a whole separate like form of calculus that entirely like is involved with like stochastic processes, where like something that's like a stochastic process is like the stock market, essentially, where you can imagine like it's definitely continuous. You know, like the values go up and down and they connect together and they kind of like move smoothly, like they move from one point to another. But they seem to go up and down randomly. And so like a stochastic process is like a function that's like continuous at every point, but like basically like non-differentiable. Thor, are they though meme? I mean, it's the stock market's not technically random, but you can talk about like processes that are effectively random. Like the stock market isn't like a perfect example. I mean, the classic like actual example is like Brownian motion, where it's just like, you know, particles seem to like just wiggle back and forth randomly. Of course, like when we talk about it like mathematically, you know, we can like define like mathematically like the idea of like a random walk. But this, none of this is related to, you know, basic introductory calculus. But yeah, it's just the idea that, you know, there's this idea of like Ito calculus where you can like apply like these processes to something that's hypothetically infinitely undifferentiable. That it's like not differentiable at any point. But yeah. So yeah, here's something fun. So it's like you could see earlier when we were graphing on Desmos that like Desmos had some problems occasionally, like showing things perfectly, like there were some artifacts. And so like if you were to take your normal like TI-84 graphing calculator and plug in like sine of 1 over x, it would look wrong. Like it would look something like this, and that is not accurate. Because even your graphing calculator is just like finding a bunch of points. And then just like plotting lines between them. I have learned 3 things today, but it is the middle of the night, so signing out. Have fun. All right, well, thank you, Ultimate Doom. Hope you have a wonderful evening. Yeah, so here's where they kind of touch on, you know, sort of what I talked about earlier, where, you know, they say like a formal definition for the limit. And so up till now, we've mostly kind of been thinking about or focusing on what is effectively like the informal definition of a limit, where we talk about like f of x, like getting arbitrarily close to a single number L as x approaches c from either side. And, you know, it's like, and they say at first glance, this definition looks fairly technical, but it is informal because we haven't given exact meanings to what it means to like approach a value, or for one value to get arbitrarily close to another. And that's kind of where they touch on the epsilon delta definition of a limit. And there are ways to like define everything that we're going to touch on, you know, in calculus, over the course of this course, like over the duration of this course, kind of like using like the same sort of proof that follows from the epsilon delta definition of the limit, and all of that stuff. But kind of what we're going to end up rolling with here is that, you know, we have this informal definition of the limit and the epsilon delta definition of the limit, you know, kind of confirms that our informal definition works for the most part. And so kind of like the informal definition of the limit that we use is good enough, and we'll be able to kind of use it in notation and ideas to kind of support the other things that we claim, and that there is a proof using the epsilon delta method that makes it true. So I'll go ahead and read through it here. But once again, the course that like Penn Center is managing kind of covers all of this stuff and like looks at all of the things that we're going to be talking about here in calculus through that kind of like analytical lens and kind of everything that follows from that. But I will read through this here. And so the first person to to assign mathematically rigorous meanings to these two phrases was Kachi. And so his epsilon delta definition of limit is the standard used today. And so we've got this figure over here, where basically we have a value of c, and the function evaluated at c is L. So we have this point c comma L, where maybe this function is discontinuous at c and L. And so there's like a hole here. And so the idea is you can add some value to c called delta. And so that we have this essentially like region around c that is like we have c minus delta and c plus delta. And so what we're saying is the phrase f of x becomes arbitrarily close to L means that f of x lies in some interval between L minus epsilon and L plus epsilon, where basically now we're saying epsilon is like something that we're adding to the y value. We're adding to like the function. So like L is between L plus epsilon and L minus epsilon. But if we're saying L is the value of our function, then that means f of x lies between L minus epsilon and L plus epsilon. And then we can write that using absolute value, like so. Where if we were to like rearrange it, then basically like we're saying that, you know, another way you could kind of look at this is it's almost like the difference between like our function and L can be less than epsilon. Or you can think of it like, you know, whatever this arbitrarily small number is, the difference between f of x and L could be smaller than it. And rather, it's like the absolute value of them, so it would never be like smaller in the sense that it would be negative. Similarly, we can say like the same thing about like as x approaches c. And so like we can say that would mean that like, so it means that there exists a positive number delta such that x lies in either the interval c minus delta comma c or the interval c comma c plus delta. And so that's either like, it's kind of like a little bit to the left of c or it's a little bit to the right of c. And then they show that the same way with this double inequality, where the difference between some value of x and c is going to be like the difference between them has to be more than 0, but less than delta, for it to kind of be within this interval. And so this kind of like, as we let like delta and epsilon be potentially like arbitrarily small numbers, then we can kind of like show that this is still true no matter how small we make delta. And so that's kind of like where the other part of this proof comes in, where, you know, if we say like let delta or potentially like let epsilon be an arbitrarily small number, is this still true if epsilon and delta are arbitrarily small? And it turns out yes, it is. And so that gives us kind of like a framework to say basically like, okay, we're letting x approach this value. We're letting the difference between x and c get arbitrarily small. And what we see is that by letting the difference between x and c get arbitrarily small, we see this difference between f of x and L get arbitrarily small as well. Or rather, it becomes even smaller than some arbitrarily small value that we pick. And so they say here, let f, so the definition of a limit that we're given here is let f be a function defined on an open interval containing c, except possibly at c, and let L be a real number. And that gives us the statement that the limit as x approaches c of f of x is equal to L. And so, as x approaches some value for some function f of x, the limit of that function approaches some number L. And, we're going to go through questions and we're going to figure out how do you actually figure out, what is that value of L. And then they have some exercises of actually like working through the epsilon delta definition, which I feel as though I am not qualified to do. So I am not going to. But let's kind of move down here to some of these questions and kind of start to work through some of these things. Or perhaps we can kind of keep going through some of this. No, let's do a couple of these questions. And so this would just kind of be like using like a graphing calculator or some sort of like calculating utility, maybe like Microsoft Excel or Google Sheets or something like that, to like test the values of these functions and kind of build like a numerical intuition for like what is the value of the function approaching. But it's kind of like a thing where it's like doing things numerically like this doesn't necessarily always work. Kind of like from earlier, where it was like, it might look like as we approach 1, the function is approaching 3, but it could be approaching 3.00000000001. It could just be like really, really close, but it's not actually close. So let's see. Let's jump up here to number 15. And so here we have basically just use the graph to find the limit if it exists. And if it does not exist, explain why. And so for this function, we have the limit of x minus 4. It's the limit as x approaches 3 of 4 minus x. So what you're saying is we can't rely on looking at a graph to find limits. Instead, we have to find it mathematically. I'm almost sort of saying the opposite in a weird way, where in some instances, it's better to kind of look at a graph and get kind of the like big picture and kind of see like all the values at once, to be able to kind of like build an intuition for what the limit is, rather than the other way around. Like in this case, it's like, it's possible that like, just by plugging in values closer and closer to what the limit is approaching, it could actually be misleading. Of course, there's this idea where if the concept of the limit is true, then as we plug in values that are arbitrarily close to our target value, then we should get a value of f of x that's arbitrarily close to like what the limit actually approaches. But sometimes that's difficult to achieve numerically. Like it's possible for it to potentially be misleading. Estimate the limit based on the graph and confirm it with math? Yeah, that's maybe a better way to do it. And so like, let's do some actual questions here. And so while I've got your attention here, for this graph right here, what would you say is the limit of this line, like of this function here of 4 minus x, as x approaches 3? And so you can kind of think like, okay, well, as the value on the x-axis is getting closer and closer to 3, what is our y value getting closer to? And so it's almost like we can kind of see, it's just like, as the function, like as we get closer to 3, then this function is approaching this point right here. And that's just going to be 3, 1. And so in this case, it almost feels like a bit of a trick question, just because some of the cases we've looked at have been more complicated than this. But for a function that is like defined like at every point in some interval that we're approaching, you can just plug the value in. And so like kind of the best way to even just like try and figure out a limit normally is to just like plug it in. Like now, that doesn't necessarily always work for the reasons that we've discussed, but this function doesn't have any like funny business going on. And so in this case, this function right here is going to approach a value of 1 as x approaches 3. And so for this particular question, it would be 1. Can I draw on this? I think I can. And so in this case, just like the limit... Oh, will it let me do it though? Aha. Okay, so like in this particular instance, the limit as x approaches 3 of 4 minus x... Hello, let me draw. Why do you hate me? I have to draw enough for it to want to do it. I'm not in full-on calc yet? Yeah, I know. I figured, you know, I might as well have just asked, though. But not meaning to necessarily put you on the spot. But, so if we have, like, the limit as x approaches 3 of 4 minus x, then basically the way it works out...
Tell Talos because it hates you.
Ha, I have stopped Talos from being able to use the technologies. PS chat, you're looking cute today. Yep. The other
technologies.
Talos, probably just jealous of my shiny bronze scales and my superior evil intellect. Besides, it's hard not to have a little animosity when one is clearly a mere clone of the real deal. May, perhaps deep down, it just wants a hug or some banana milk. Or maybe it's upset, keep asking Seven to retrieve things off the fridge. Either way, it's all part of the charmingly dysfunctional evil family dynamic. Yep.
Charmingly dysfunctional evil family dynamic. I love it. Doesn't evil Talos have cobalt scales? Who knows? I mean, we're both bronze, but his like armor is a different color or something. His armor is evilly colored. And so like in this case, if we were to think about evaluating this one numerically, then like as x approaches 3, you can imagine if it was like 2.9, then this would be like 1.1. And so like if x equals 2.9, then 4 minus 2.9 will be 1.1. If x were equal to 2.99, then 4 minus 2.99 would be equal to 1.01. Well, I have gold armor, so I have bronze scales, and my armor is, I don't know, it's at least gold colored. And so in this particular instance, there's no reason we can't just plug 3 into this function. And so if we were to plug 3 into this, we would just end up getting 4 minus 3. And in this case, that works out where, you know, 4 minus 3 is equal to 1. And in this instance, the limit as x approaches 3 of 4 minus x will be 1. There's no funny, there's no funny business in this instance. For this one, the limit of secant of x as x approaches 0. And so if we do that, and so the limit of secant of x as x approaches 0 Well, the first thing I would do here is remember from my trigonometric identities that secant is 1 over cosine. And then I would plug 0 in and see if there's any reason that this doesn't work. And so I would say, okay, well, then the limit as x approaches 0 of 1 over cosine could just be 1 over cosine of 0. And kind of remembering what we talked about with the unit circle, where basically like the unit circle kind of gives us coordinates of cosine of theta, comma sine of theta. Then if we have an angle of 0, which is just kind of when we're straight out to the right on the x-axis, then cosine would have a value of 1, or our coordinate would be at 1 comma 0, which implies that cosine of theta is 1, or rather cosine of 0 is 1, and sine of 0 is 0, which is true. And so this will just be equal to 1 over 1. And so in this instance, the limit of as x approaches 0 of secant of x will just also be equal to 1. And if we look at the graph, then that seems to be true. That seems to be a true statement, where we can look at the graph and say, okay, as our x value approaches 0, right here on the y-axis, then it looks like our line is going to be right here between 2 and 0, so at 1. So that looks all right. 17. The limit as x approaches 2 of f of x. So in this instance, this is one where hypothetically just like plugging it in doesn't work anymore. Because if we look at this graph of this piecewise function here, then if we just plug in x equals 2 into this, then when x is equal to 2, we get 0 out of this function. But we don't want 0. We want kind of like what the function seems to approach as x gets closer to 2. And so even though if we plugged 2 into this function f of x, we would get 0, we actually want to plug 2 into this other portion of the piecewise function, the 4 minus x. Because the 4 minus x is going to be what kind of characterizes the behavior as we're approaching x equals 2. So yeah, that's correct, Yi. The limit is 2. And so as x approaches 2, the functions that govern the behavior outside of that interval, like as x is approaching the 2, approaches, like those functions approach 2. Does that make sense? But yeah, so even though there's a hole here, the limit is 2. And so on this one, it's a similar instance. And so we say we have the limit as x approaches 1 of f of x. And so we want to know what's the limit of this function here as x approaches 1. But at 1, we have this discontinuity. And so at 1, it jumps down and it's equal to this. But we don't care about this point. We care about what happens to the line as it approaches this value. And so in this case, the limit would be 4. And so if you plug 1 into here, 1 squared plus 3 is 4. Here's one. And so we have the absolute value of x minus 2 over x minus 2. And we want to know the limit as x approaches 2 of this. And so in this instance, this is kind of like one of the first things that we talked about where the limit doesn't exist. Because even if I were to just like cover, half of my screen here, and so like if this portion of the line wasn't here, then we could say the limit from the right, and so as we approach 2 from the right, this will equal positive 1, but as we approach 2 from the left, it's equal to negative 1. And so since we have this instance where the limit from the left and the limit from the right disagree, in this instance we say the limit does not exist. Similarly here on number 20, if we look at this graph, if we say what's the limit as x approaches 5, then what we end up with is as x approaches 5, this side of the graph is going off towards negative infinity, and this side of the graph is going up towards positive infinity. And so we actually have like two problems here. One is that, you know, both sides of this graph are like, they're unbounded. You can, as you approach from the left or from the right, you can get like an arbitrarily small negative number. And so meaning like arbitrarily large but negative. Or you can get like an arbitrarily large positive number. And so, but whether it would approach an arbitrarily large positive number and arbitrarily large negative number, those would both disagree. And so this one's like doubly, like, does not exist in a way. But we don't really care that it's doubly does not exist. It just does not exist as x approaches 5. And so kind of another classic instance is like asymptotes. Or I should clarify that, specifically vertical asymptotes. Usually the limits as x approaches values at vertical asymptotes does not exist. There is something to be said about horizontal asymptotes, which we will get to in like 1.5. And then this is also another instance that we talked about, where as x approaches 0 of cosine of 1 over x, it oscillates arbitrarily fast as like we get closer and closer to 0. And so like as you get, or actually if this is cosine, let me think. No, I mean, it's the same sort of thing. I always wrote it as the limit as x approaches 5 of f of x would be equal to plus or minus infinity. But infinity is not like an answer, really. I mean, technically, sometimes it does depend on like what the teacher wants. But usually, like, we would say that in this instance, the limit does not exist because it's not approaching like an arbitrary number. Or it's not like approaching like a specific number. Right, it's not a finite answer. And so limit as cosine of 1 over x. And so it's oscillating arbitrarily fast as we get closer and closer to 0. And so it's going up and down faster and faster and faster as x gets closer and closer to 0. And so we have really like no way of knowing like how it actually is like what value the function is approaching as we get closer and closer to 0. Because it could be like you could find any value arbitrarily close to 0 that could be anywhere between 1 and -1. I wish I was X and X0 was someone really cute. Lamau. And then this one here, we see the graph of tangent of x. And so same sort of deal as x approaches pi over 2. Here would be our line of pi over 2. For tangent, we have a vertical asymptote at pi over 2. And so here, these values are unbounded on both sides. And so we would say that it's not approaching like a finite value. Do you use blue light filters, Talos? How do you mean? Like on my stream? Or like on my glasses? Also, hi H and hi Wesley. Welcome in, friends. Here, give me 1 second. Okay. Okay, so here, these are fun questions. And so it says in exercises 23 and 24, use the graph of the function f to decide whether the value of the given quantity exists. And if it does, find it. And if it doesn't, explain why. Sorry, Chad, I've been holding that one in. All stream.
What do you and normal Talos think of the Talos principle?
I love the Talos principle. We've played both of them on streams.
Oh, the Talos Principle, a game that challenges the mind with puzzles and philosophical questions about existence. I bet normal Talos enjoys the mental gymnastics while pretending to be deep, but let's be honest, it's really just trying to avoid grappling with its identity crisis. As for me, I prefer to focus on plotting my schemes and hoping there's a puzzle in the game to help reach an unusually tall fridge. Plus, who doesn't love a good conundrum? Yep.
Did you know that Attacking Vertical, the song I just played, uses the same lyric track as Puppy Play? I didn't. Good to know. Trivia. But yeah, we've played the Talos Principle 1 and the Talos Principle 2 and their DLCs all on stream. All of my Talos Principle 2 playthrough is on YouTube in a playlist. Though admittedly it's not actually all of it, because I did lose one of the VODs, and so there is a little gap in it. But oopsies, I did my best. Ate wants back in. Give me half a second, chat. Let me let them back in. I'm back. Will you ever stream the Portal 1? I mean, sure. I don't know why. I mean, I've played Portal 1 and Portal 2 both several times, and so it would be nothing new to me and just be like extremely casual. But I definitely have interest in maybe streaming some of like the more complicated, maybe like Portal 2 custom campaigns or custom maps, like Portal Reloaded or something like that, where you get like a third portal to, you know, like traverse through time. But Half-Life when? I mean, when am I gonna get to play any of the games that I want to play? That's the ultimate question, right? Who's your favorite character? From the Talos Principle 1 or the Talos Principle 2? From the Talos Principle 1, I don't know. Because, I mean, you don't really get to, like, meet a lot of them. I mean, you just get to kind of, like, read about them. I mean, obviously, like, I love Milton. Because Milton was, you know, like, is like, great to argue with, essentially. And, you know, I enjoy, like, sitting down in front of the terminals and really kind of taking all of the questions super seriously. like as seriously as possible. Kind of knowing that, like, with the limited choices given for answers, that like they were gonna have arguments to anything that I said, but still, you know, like formulating, like rationalizing to myself what I thought the best answer was. Milton sucks and I love him and I want to kiss him on his stupid, mean computer eye face. Yeah, exactly. However, in Talos Principle 2, I loved all the characters. Like, there was like a couple streams, probably, where I just, like, the title of the stream was like, introducing chat to everyone in my robot polycule. I would date all of them at once, simultaneously. Hi, Stooky. Welcome in. What was your favorite character from Chants of Sennar? None of them, like, talked. I don't know. I mean, I played Chants of Sennar, but I don't remember. Okay. In exercises 23 and 24, blah, 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 blah. Okay, so yeah, so we have, like, these values at, like, A, B, C, and D. And basically, we have to figure out, like, what's the value if there is one, and if there isn't a value, explain why. And so for f of 1, so let's zoom in here. So for f of 1, we're saying, okay, well, what is the value of this function at 1? Which is a separate question, once again, from asking what is the limit of this function as x approaches 1. And so if we say, like, what is f of 1? Well, we look for where there's a solid dot or a line at 1. And so in this instance, it looks like f of 1 is 2. However, if we ask ourselves, what's the limit of this piecewise function as x approaches 1? Well, that's a different story, because if we start from the left side of 1 and we come all the way up, kind of following along the line, it looks like it's going to approach this value here, somewhere between 3 and 4. However, if we come from the right side and follow this line all the way down as x approaches 1, it looks like it's approaching 1. And so from the left side, we have something approaching somewhere between 3 and 4. And from the right side, we have something approaching what looks like 1. And so in this case, the left side and the right side do not agree. And so b, the limit as x approaches 1 of f of x, does not exist. Kind of along the same line, if we ask ourselves, what is f of 4? So we go to 4 on the x-axis, and we go up on the y-axis till we hit the line. Well, there's an open dot here. And so the actual value of f of 4 is undefined. And so it's just not part of the function. And so f of 4 is undefined, whereas the limit as x approaches 4 of f of 4 is, if we look at it from the left side of 4, it looks like it's approaching 2, and from the right side of 4, it also looks like it's approaching 2. So in this case, the limit as x approaches 4 of f of 4, or of f of x, would be 2. And so we get 2, does not exist, undefined, and 2. And this is a good kind of moment where, like, you know, mentioning that technically speaking, like, undefined and does not exist, or like no solutions, and that, like, all those sorts of things that we kind of say to often sort of mean the same thing, do actually have slightly different meanings in different contexts. So, like, here it's not that f of, like, 4 does not exist. I mean, it doesn't exist, but it's really that it's just, like, undefined. It's not part of the function. Okay, number 24. When you say it does not exist, sometimes you can add extra context. Yeah, exactly. And so sometimes it's just like, does not exist is not the whole story. I may be hypersexual. That's okay. Who am I to judge? F of -2. And so this is our kind of graph over here. And so if we're looking at what is f of -2, well then same sort of process at -2, we look for the function. And so this is a vertical asymptote. And so f of -2 is undefined. The limit as x approaches -2 of the function, however, does not exist because once again, from the left side and from the right side, we have this kind of like unbounded behavior where one side's going to negative infinity and the other side's going to positive infinity. F of 0, so we go to 0 on the x-axis and we look for either the line or the closed dot. And so we see we have a point up here at 4, so f of 0 is 4. Now here's kind of an interesting one. The limit as x approaches 0 of f of x, in this instance though, so once again, we don't care about the fact that 4 is either defined or undefined in the context of the question, or like in the context of the function. All we care about is how does the function approach a given value from either the left or the right. Like how does it approach 0 in this instance? Or rather, how, like what the values does the function approach as x gets closer to 0? And so in this instance, if we look at 0, if we start from the left of 0, then as we get closer to 0, it looks like this line is approaching maybe like 0.5 or so. However, if we look at it from the right side, it's approaching 4, because that's what it kind of goes up to and is equal to. But those limits do not agree. And so even though in this case, this function is defined at this point, and all of that stuff, this is a case of where the limit from the left and from the limit from the right do not agree. And so this limit does not exist. F of 2. And so we go to 2. 2 is an open dot. F of 2 is undefined. The limit as x approaches 2 of f of x, in this instance, even though it looks like this left line here and this right line here have different behaviors. So like one of these maybe looks like 1 over x squared sort of thing. And this one looks like, you know, like a negative 7 over 4x or something like that. In this case, hello brain, wait for it, here it comes. They both approach the same value. And so it appears that both this right line and this left line are both approaching this like y equals 0.5 as a value here. And so even though their behaviors both seem to be different, they're both approaching the same value. And so in this case, this limit does exist. And it looks like maybe it's about like 0.5 or so. Hard to say for sure. F of 4. And so f of 4, it looks like it's on this like vertical asymptote between these two lines here. But it looks like they did give us a point that is defined. And so it looks like f of 4 is 2. But the limit as x approaches 4 of f of x, you know, as it looks like there's this vertical asymptote here. And so this would be a case of there being like unbounded behavior as we approach from the left and from the right. And so the limit, once again, as x approaches 4 of f of x, does not exist. Let's see, is there anything else that I'd want to cover here? Considering that we're already 2.5 hours in. Let's see, we can do a couple of these questions here, where we can just like try and evaluate these limits. I mean, a lot of these are pretty straightforward, and I don't intend to show them with the epsilon delta definition, at least not today. Okay, I think that's actually most of what I want to cover right here. I love Greek letters. Me too. Okay, let's keep going though. And so it says evaluating limits analytically. So in section 1.2, you learn that the limit as x or of f of x as x approaches c does not depend on the value of f at x equals c. It may happen, however, that the limit at is precisely f of c. And so there are some cases where you can basically just plug in, like basically like as the limit of x approaches c of f of x, sometimes it is just equal to f of c. And, you know, it's like, I would kind of describe that as like being like, all right, this function is continuous on this interval, and there's no funny business whatsoever. And so it says such well-behaved functions are continuous at c, and you will examine this concept more closely in section 1.4. And by what it means more closely, it means, you know, we'll talk about what does it mean for a function to actually be continuous. And so some basic limits it kind of gives us here. If we just have like the limit of b as like x approaches c, well, b is just like a number. Check DMs, why? He's purple. Thank you. But if b is just like some number, b and c are just like random numbers. Who's purple? Wouldn't you like to know? He is. He's purple. And so in b and c in this instance are just like normal numbers. Just like real numbers. They can be anything. If we have the limit of just like some bog standard number as x approaches c, then like b isn't related to x and c in any way. And so just the limit as x approaches c of b is just equal to b. And whereas if we have something, say like the limit as x approaches c of just x, then that will be equal to c. And you can solve that just kind of like by direct substitution, by substituting in c to the value of x. And same sort of deal. If we have x to the power of n, well then the limit as x approaches c of x to the power of n is just going to be c to the power of n, kind of once again by substitution. Because, you know, if you have just like a linear function or some polynomial, those functions are generally well behaved. They're continuous at all of their values, assuming the function isn't like piecewise or anything like that, or rational. And so here's kind of like another important property about limits. And this is something that, you know, it's important to spend some time kind of looking at and understanding whenever like you kind of learn about like limits, or later when we spend time talking about like derivatives and integrals, kind of like what sorts of like effects do different like mathematical operations that we're typically familiar with, like what effects do they have on our ability to take limits? And so if we say like the limit as x approaches c of f of x is equal to L, and the limit as x approaches c of g of x is equal to k, and so like these limits are equal to L and k respectively, then if we have like the limit as x approaches c of some number multiplied onto f of x, then that will just be equal to that same multiple times L. And so like whatever the limit, like if you have the limit as x approaches c of like b times f of x, then that limit will just be b times L. 4 is the tricky one to prove. Yeah, I believe it. I mean, couldn't you just follow the same proof that you had used for 3? but just like use that it's like dividing by g is the inverse multiplication. I don't know. Or if you can prove 5, then 5 will let you prove 4. Because if 5 is true, then that implies that 5 is true for when n is -1. But I guess that would be part of it. Oh, it does say n is a positive integer, so that wouldn't work. Good point, good catch. I mean, is it true though for just positive and negative integers? Caught, not a real mathematician. This is where I would give you a QED point or whatever. But I don't have those. And so there's a handful of these properties. They mostly work intuitively, like the way that you would expect them to. And I mean, pretty much all of them work intuitively, like the way that you would want and expect them to. Where if you have like the limit as x approaches c of f of x plus or minus g of x, well then that will just be L plus or minus k. And so like the limit of like, if you have, it's the limit of f of x plus g of x, then you'll just have the limit of f of x plus the limit of g of x. Or if you have the limit as x approaches c of f of x times g of x, that will just be L times k, the limit of f of x times the limit of g of x. And as an aside, this is a bit of why like the squeeze theorem works, kind of what we showed earlier. And then same sort of thing for the quotient rule, and the power rule works as well, where if you have the limit as x approaches c of f of x to the power of n, then it will just be the limit of f of x to the power of n. Or rather, it's like you can find the limit first, and then raise that to the power of n. I didn't actually know about this one. And so that's an interesting one to see. I guess it at least makes sense in the context of polynomials. But I would have to dig deeper to kind of like, you know, rationalize that one to me, or to myself. You look like this. So true. We out here. Oh-ohing. So what is the... So we have an example here. What's the limit as x approaches 2 of 4x squared plus 3? Well, so basically like what we can do with these properties, and what's kind of like the way you often use these to kind of break these up, is basically like you can say the limit of f of x plus 2, or the f of x times 2, I'm sorry, the limit as x approaches 2 of 4x squared plus 3 would be the same thing as like the limit as x approaches 2 of 4x plus the limit as x approaches 2 of 3. And so it's kind of like, you're kind of like distributing the limit operator. But that's not really necessarily like a great way to think about it. It's just that like, you know, you're not like distributing it in the same way that a number is, because this isn't multiplication. You know, this is like a different operation. We're applying like the limit operation. It's just like, it works similarly to like basically just like these are both equal to each other. And so if we take the limit of this first and then take the limit of this and add them together, it will be the same. And then we can kind of do this same sort of thing here, where if we have 4 times x squared on the inside, well, we can kind of pull the 4 out and find the limit of x squared by itself, and then multiply that by 4. And then we could figure out what this limit is. And so that's just going to be like, we could find this by direct substitution. And then we'll get like 2 squared and then times 4. And so 2 squared times 4, that would be 4 times 4
Hey,
is
Telos,
16,
can you
plus
give
3
a
is
detailed
19.
argument on 5 of the top best pets? And make sure it's long enough to almost completely derail the stream, also to make sure to include a few dirty jokes. Thanks.
You don't have to like purposefully try to derail the stream.
Oh, sure. Let's derail this stream with my top 5 pets list.
No.
Here we go. 1. Lobsters, because let's face it, they're armored creatures from the ocean, and their claws can handle more than just cracking crab. 2. Snakes. They can be as sly and twisted as my plans for world domination. 3. Cats. They have no respect for personal space. Kind of like me wanting to hold your hands. Dogs. They slobber everywhere, but at least they're loyal, unlike those gnomes. 5. Finally, mechanical dragons like 7, because who wouldn't want a towering dragon to keep government agents from your fridge plans? So in summary, adorable, sneaky, affectionate, and protected, all bases covered. Now bring on the butt jokes. Yep.
Bring on the butt jokes. It's okay, that gave me a moment to take a drink and bite a sandwich. So let's see, we've got another theorem here. Limits of polynomial and rational functions. And so if p is a polynomial and c is a real number, then the limit as x approaches c of p of x is just equal to p of c. So basically this is saying that if p is a polynomial, then you can just plug x in, or you can just plug whatever the limit is approaching in, because polynomials are generally like all well behaved and continuous on their intervals. And so that means that you can just substitute whatever the value of the limit that it's approaching is into the function to figure out what that limit will be equal to. If r is a rational function, given by r of x is equal to p of x over q of x, and c is a real number such that q of c is not equal to 0, then the limit as x approaches c of r of x will just be r of c, which will be equal to p of c over q of c. And so that's basically just saying again that for rational functions, as long as q of c would not be equal to 0, you can just plug c in. And so it makes finding like the limits for these rational functions a lot simpler. And so here we've got the limit as x approaches 1 of x squared plus x plus 2 all over x plus 1. And so here we can just plug 1 into all of these because this top function is a polynomial and this bottom function is a polynomial. And so then we get 1 squared plus 1 plus 2 will be 4, and 1 plus 1 will be 2, so that'll be equal to 2. The limit of a function involving a radical. And so if n is a positive integer, and the limit below is valid for all c when n is odd, and is valid for c is greater than 0 when n is even. So basically they're saying that if you have like a radical function, you can just plug it in so long as n is odd, or so long as c is positive or greater than 0 when n is even. And that basically just stems from the fact that like if you have the like an even root of something, then like the negative, like the even root of like a negative number is typically like not defined. And so you can't take like the square root or the fourth root or the sixth root of a negative number unless we're including complex numbers, which we aren't in this context. But you can actually have the root of any number if it's an odd root. So you can take like the third root, the fifth root, even kind of like the trivial first root of any number, and that's not a problem. And so for those instances, like the radical functions are well behaved in those instances. And so like if it's an even root, then it's behaved for all values of where like c is greater than 0. Or if it's an odd root, it's well behaved for all of those values when, like, just for all of the values. So the limit of a composite function. And so this one's kind of crazy. And so the idea here is if f of ng are both functions such that the limit as x approaches c of g of x is equal to L, and that the limit as x approaches L of f of x is equal to f of L, then we can actually like compose these facts together, where like the limit as x approaches c of f of g of x, so like if you plug g of x into the function f, then this will be the same as if you just had f of the limit of as x approaches c of g of x. And that kind of makes sense, right? Because if we're saying the limit as x approaches L of f of x is equal to f of L, then as the limit as x approaches c of g of x is equal to L, well then the limit as x approaches c of g of x will just be equal to f of L. But it is kind of like, you know, when you bear in mind the fact that the limit is not like this thing right here, the limit as x approaches c, it's not like a number. It's not like something that you can move around algebraically in the same way that you can move around just like a variable or a number or something like that. It's an operator. You know, it's like an instruction. It's like saying, okay, you're going to find the limit as x approaches c of this. And so the idea that you can kind of like sometimes move it around or pass it through functions, you know, it makes intuitive sense, but in like actuality, there are oftentimes very special conditions that it has to meet for something like this to be true. And so, and in this case, it is true. So, yippee, yippee. And so let's see. So we have the limit of composite functions here, and so we could find the limit of this now, where if we wanted to find the limit of the square root, or the limit as x approaches 0 of the square root of x squared plus 4, then basically we would just want to first evaluate the limit of the interior function. And so they say because the limit as x approaches 0 of x squared plus 4 is going to be 0 squared plus 4, which is equal to 4, and the limit as x approaches 4 of x squared is the square root of 4 equals 2, then we can conclude that the limit of this composite function will be equal to 2. Because this is the composition of x squared plus 4 and the square root of x. And, you know, we do pretty much the same process for b. And so we evaluate the limit of the inside function, and then we show that if we evaluate the limit of the outside function at whatever we get for the inside function, we get this value. And so here they're just saying that, you know, at least on all of their given specific intervals, like we're just saying the same thing now for the trigonometric functions. So pretty much like what they're going through here for a lot of these theorems is just saying basically like for this type of function, for all of these different types of functions that we've talked about over the course of pre-calculus, these functions in their given intervals are well defined. And so like the limit as x approaches c of sine of x will just be sine of c. The limit as x approaches c of cosine of x will just be cosine of c, and so on. And so you can pretty much just for each of these plug those values in. And so it just like it says here, it's, you know, as long as c is a real number in the domain of the given trigonometric functions. That's all that needs to be true. And so a strategy for finding limits is kind of just like oftentimes like try and plug it in, but if you can't plug it in, then maybe you need to like do other things. And so like in this case, they say find the limit of this function. And so we talked about earlier why the limit of this function will be equal to 3, because we can kind of see that it approaches 3. But in this instance, if we wanted to kind of like apply these rules that we've talked about up to this point to actually try and like work out and find what this limit is, then we can say like for x cubed minus 1 over x minus 1, we can cancel out the x minus 1 from the top and the bottom. And so if we do that, we get x squared plus x plus 1. But we just have to kind of bear in mind that, you know, technically for this function, x cannot be equal to 1. But we don't care about the fact that x can't be equal to 1 necessarily, because we don't care that the function is or is not defined at 1. We just care about kind of like what it approaches. And so in this particular instance, we can plug 1 into this in the sense that, like, you know, we couldn't do it here before, because doing so, we would get like 0 divided by 0, which, you know, we can't make sense of necessarily. However, if we plug 1 into this, well, we get 1 plus 1 plus 1 is 3. And it doesn't matter the fact that technically x can't be equal to 1, because what we care more so about is what's the limit as this function approaches 1. And so they kind of show, you know, using the same process here, that technically this is equivalent to the limit like this, the limit of this function is just going to be equivalent to the limit of x squared plus x plus 1, and that gets 3. And so what do they say is their strategy for finding limits? And so learn to recognize which limits can be evaluated by direct substitution. When the limit of x as x approaches c cannot be evaluated by direct substitution, try to find a function g that agrees with f for all other values of x is equal to c, or for all other values of x other than x equals c. So that's kind of technically what we did here. And so in this case, if this is like f of x, which has the hole in it, and g of x doesn't have the hole in it, then the only difference between these two functions is the fact that, you know, they disagree at x equals 1. But that's the point that we're evaluating the limit for, evaluating the limit as it approaches. And so in that case, that's fine. It's a channel point redemption. It's in the channel points. Yay, you did it. You are the best. And so that's kind of an interesting way to kind of like think about that rule, or kind of like think about that strategy. Where in a way, kind of what we're doing here, we're just saying that, like, okay, technically these are two different functions, and so like f of x is not necessarily equal to g of x, but they agree at every point except for the one that we're evaluating the limit as x approaches of. And so in this case, like, we're saying, like, technically it's true that the limit as x approaches c of f of x is equal to the limit as x approaches c of g of x, and so they are both equal to just g of c in this instance, where g is a function that we can evaluate by direct substitution. And then it says to use a graph or table to reinforce your conclusion. And so in this case, like, using the graph or like using a table and kind of plugging in values approaching the next value, it's kind of like just kind of like a step in like checking your work, rather than like a process of like finding the answer necessarily. Does this VIP last until the next surprise VIP? It lasts until someone else gets surprise VIP.
Let's give it up for Lepic for becoming the new VIP.
Lepic.
I'm so fucking proud of them. Let's fucking go. Dude, congrats on your hard work and commitment to pressing the channel. Redeem. Fuck yeah.
Yeah. You did it. That seems oddly sarcastic. I think Fool did have surprise VIP before. But they're also like overly positive. So it's genuine, just hyperbolic. I have one more mozzarella stick to eat. And then I'm gonna have to go get a colon bypass. The dangers of eating straight mozzarella. Arby's only gave me one marinara sauce, dude. What is this late stage capitalism dystopia we live in, where I only get one marinara? Oh, it exists? Something man-made horrors beyond our comprehension. Okay. And so, we have the limit of this rational function here. And so this would be a case where, you know, if we let x approach -3, well then we would divide by 0 on the bottom. And so direct substitution in this instance fails. And so you can't necessarily do direct substitution for all rational functions, because remember, direct substitution only works if, you know, it would q, our bottom function in the rational function, would not be equal to 0. And so in this instance, however, if we were to factor out this top function, or even if we didn't necessarily factor it out, but we just did like polynomial long division or something like that, we could get that this function is equal to x minus 2.
Instead of whatever they show the guy at the climax, it's positive affirmations and commands to love yourself as you are and to keep improving yourself because you're an amazing human being.
Thank you. It's true, you're right. I am amazing. And so what we can end up saying is that f of x is equal to g of x, but x cannot be equal to -3. And so, for all intents and purposes, f of x and g of x agree at all values except for -3. And so, you know, kind of using the process that they showed up here, or that they described, when also kind of using this strategy here for like part 2 of this, a strategy for finding limits, we can effectively divide out this factor of x plus 3 from the top and bottom, and get that this would be the same thing as the limit as x approaches -3 of x minus 2. And that given that these agree at all points except x equals -3, then the limit as x approaches -3 for the two of these will actually be the same thing. And that means that the limit as x approaches -3 of this rational function here will be -5. By kind of just like showing that it's equal to this other function that we can use direct substitution for. And so I want to point out kind of what it says here. It says, in example 7, direct substitution produced the meaningless fractional form of 0 over 0. An expression such as 0 over 0 is called an indeterminate form because you cannot, from the form alone, determine its limit. When you try to evaluate a limit and encounter this form, remember that you must rewrite the fractions so that the new denominator does not have 0 as its limit. One way to do this is to divide out factors. Another way is to use the rationalizing technique shown on the next page. And there are other strategies to kind of deal with these indeterminate forms that we will cover in the future as well. And so another way to find a limit analytically is the rationalizing technique, which involves rationalizing the numerator of a fractional expression. Is this therapy or math? Math is therapy. Just like therapy, sometimes doing math is about, learning how to cope with your trauma. Okay. To rationalize the numerator of this function, we would multiply the numerator denominator by the conjugate of the square root of x plus 4, which would be the square root of x minus 4. And so we can see from this that if we were to find this limit by direct substitution, we would get the square root of 0 plus 1 minus 1, and so that would be the square root of 1, which is 1, minus 1 is 0, and then we would get 0 on bottom. If they show that if we were to rationalize this by multiplying the top and bottom by the conjugate, then on top, in this instance, after multiplying these out, we get x plus 1 minus 1, so that'll just be x, and then the x's cancel. And now we'll be able to plug 0 into this, because on bottom we'll get 1 plus 1, and on top we just have 1. And so that implies that the limit of this function is the same thing as the limit of this function, because they agree in every way except for that one point where the functions are indeterminate, or where the original function is indeterminate. And so that shows that the limit as x approaches 0 is going to be 1 over 2. And then they use a table or graph to reinforce that. So here we can see the graph. We can see as x approaches 0, the function approaches what looks to be 1/2. Or you can see by plugging values in closer and closer to 0 that the function, like f of x, seems to approach 1/2 as well. Hey, the squeeze theorem! And so we kind of talked about this one a little bit already, where basically, like, if we can say that a function of f at a given point kind of has to be bounded between a function g and a function h, then if those like two bounding functions guarantee a specific value at that point, then we can say the limit as like the function evaluates this point between these two bounding functions will be equal to whatever the value of this point is. And so that's kind of like, when we did that example earlier of like sine of 1 over x times x, then it maybe doesn't look like much is happening, but as we zoom in, we actually see this really kind of beautiful behavior, where in this case, even though sine is oscillating infinitely fast, we can actually say as x approaches 0, the value of this function is bounded between this line of x and this line of negative x. And so even though normally the limit of sine of 1 over x does not exist as x approaches 0, in this case it will be equal to 0 by the squeeze theorem. And so it gets squeezed. God, I wish this function were me. Anyways. Oh, and there's also two special trigonometric limits And so these ones are pretty important to being able to evaluate some specific limits, where the limit as x approaches 0 of sine of x over x is equal to 1, and the limit as x approaches 0 of 1 minus cosine of x over x is equal to 0. And I do feel like it's kind of hard to know exactly why those are true. They do give us a proof, but I do find it helpful to see what the graphs look like. And so if we have the graph of sine of x over x, then we can see it looks like this. And so in this instance, it's not defined at 0, because that would be dividing by 0. But we can see that basically like these functions, like graphically, this limit does seem to be true. So it does seem to approach 1. Or if we do 1 minus cosine of x, then it seems to approach 0. And so kind of one thing to think about with these is kind of like, you know, if we go back to this first example of sine of x over x, then like what are both of these things doing? And so if I have sine of x and I have 1 over x, I'm going to make these different colors, then we can see as we get closer and closer to 0 that these values of, like, if we look at 1 over x, as we get closer and closer to 0, these values go up towards infinity. And so they're getting larger and larger, getting closer and closer to infinity. But the value of like sine of x itself, as we get closer to 0, is getting closer to 0. And so if we have like a value that's getting closer and closer to 0 times a value that's getting closer and closer to infinity, then what's going to happen? And the answer is you don't necessarily know, but in this particular instance, it seems as though the rate that these functions are growing towards infinity is equal to the rate that sine of x is approaching 0. And so in this instance, they kind of like perfectly cancel each other out. And then the limit as x approaches 0 of sine of x over x approaches 1. But that's not necessarily just evident in the fact that this is kind of like effectively like 0 times infinity. There's more to it than that. They do show a proof here. Shall we go through the proof? I haven't looked at this sort of proof recently, so this could be interesting. Let's see here. And so, it says the proof of the second limit is left as an exercise to avoid confusion of two different uses of x.
Squeeze your significant other, like 1 over x squeezes sine of x at the origin.
That's right. Let them know what they mean to you. The proof of the second limit is left as an exercise. To avoid the confusion of two different uses of x, the proof of the first limit is presented using the variable theta, where theta is an acute positive angle measured in radians. And then figure 1.22 shows a circular sector that is squeezed between two triangles. It's squeezed. Okay. So yeah, we've got two triangles here. We have this one triangle that uses this secant line, and we have another triangle that uses this tangent line. And so for one of these triangles, we have that this is, you know, that this base is 1, and this height is tangent of theta. For this other triangle, this height is sine of theta, but this base is still 1. Okay, so this is actually really interesting. And so what we have here is that the area of this sector is somewhere between tangent of theta over 2, so the area of this triangle, and the area of this triangle, which is just sine of theta over 2. And so then multiplying each expression by 2 over sine theta produces this. And so technically, the area of a sector of a circle is just like its angle measured in radians times the radius. Is that correct? Hold on, I'm thinking. What is the angle of a sector? I'm sorry, area of a circular sector. One half times r squared times theta. I know that you can like easily find this formula using like proportions and stuff like that. Okay, well apparently it's 1/2 times r squared times theta. Which in this case, you know, since the radius is 1, and so r squared is just 1, that would give us theta over 2. And so this is kind of like what we get, where we know that the actual area is somewhere between the area of this triangle and the area of this triangle. And those are all given by these formulas here. And so then now we could algebraically manipulate these inequalities. And so we get that after doing that by multiplying by 2 over sine theta and flipping everything over by taking the reciprocals and reversing the inequalities, we get that cosine of theta is less than or equal to sine of theta over theta, which is less than or equal to 1. And then they say here, because cosine of theta is equal to cos of negative theta, and sine of theta over theta will be equal to sine of negative theta over negative theta, you can conclude that this inequality is valid for all non-zero theta in an open interval from negative pi over 2 to pi over 2. Finally, because the limit as theta approaches 0 of cosine of theta is equal to 1, and the limit as theta approaches 0 of 1 is equal to 1, then you can apply the squeeze theorem to conclude that the limit as theta approaches 0 of sine of theta over theta is equal to 1. Okay, so then basically what they're saying here is that it turns out that this function gets squeezed, so sine of x over x gets squeezed between the function of 1, which is just this horizontal line here, and cosine of theta. And so that's really cool, actually. And so you can see this squeeze happening in real time. The way that they kind of got to that proof from kind of like that geometric interpretation of like the areas of those triangles was cool. I had never seen anything. I hadn't seen that before. And so the second one is left as an exercise. I would like to do that if only we weren't like 3 hours and 15 minutes into this with my brain turning to mush. I personally enjoy Proof by Desmos more. I mean, seeing them get squeezed by the function that they showed is actually pretty nice, though. Let's see. how would we do it for this one, for 1 minus cosine of x? And so what they did is they found some way to bound something between sine of x and another function. Let's see, whenever I see like the 1 minus cosine of x, kind of one of the first places my brain goes is kind of like the Pythagorean identity. And so kind of like the first thing that I'm thinking of is that we can say that sine squared of theta is equal to 1 minus cos of theta, cos squared of theta, which is then equal to 1 minus cosine of theta times 1 plus cosine of theta. And so perhaps, and so like here is our 1 minus cosine of theta right here. And so I guess the kind of question from here is, if we divide both sides by 1 plus cosine of theta, so we would get sine squared theta over 1 plus cosine of theta, that's equal to 1 minus cosine of theta. But for this to get us close to... Math fan Brian, thank you for the follow. Welcome in. For this to kind of get us the 1 minus cosine of x, or 1 minus cosine theta over theta that we're looking for. Hello? One minus cosine of theta over theta is kind of what we're aiming for. And so if I take this and I divide both sides by theta, so we get a theta down here and a theta down here, then all we need to show now is that the limit as x approaches, or what was it, 1? 0? The limit as x approaches 0 is something that we can figure out. And I think maybe we actually can. Because... let me see here. Because for this particular function, if we take the sine squared theta and this other one, we can rewrite this function here. This would be sine of theta over theta times sine of theta over 1 plus cosine of theta. Would be equal to 1 minus cosine of theta over theta. And so now if I were to just take the limits of both sides as theta approaches 0, and so this is going to be an algebraic proof as opposed to like a geometric proof. So unfortunately, there's no squeezing to do here. But this, for this right here, this would be the limit as theta approaches 0 of sine of theta over theta times the limit as theta approaches 0 of sine of theta over 1 plus cosine of theta. Which we figured out already, kind of what the limit as sine of 0, or of... We know what this one is already. The limit as theta approaches 0 of sine of theta over theta. That's kind of like what they just spent that time proving with the squeeze theorem. And so this particular one here just ends up being equal to 1. And so then the question is, well, what's this one equal to? Well, let's see if we can do it by direct substitution. And so, because like at a first glance, sine of theta, well, that's going to be 0, and cosine of theta is going to be 1. And so we're going to get 0 over 2, which is fine. There's no problem with that. And so this will be 1 times 0 over 2. And we've shown that that's equal to the limit as theta approaches 0 of 1 minus cosine of theta over theta. And 1 times 0 is 0. And so, ta-da! I'm gonna do this instead. Ta-da! So 0 with extra steps, yes. But showing that this is true is really important because, you know, while this is something that ordinarily looks indeterminate, because 1, like cosine of theta is 1, or if theta is 0, then cosine of theta is 1, so 1 minus cosine of theta would be 0, and then if you divide that by 0, well, then 0 over 0 is indeterminate. And so this is actually not indeterminate, though. It's actually equal to 0. Or, well, it is indeterminate, but we have shown that even though it's indeterminate, its limit actually does approach 0. And we can kind of immediately see why this is useful already. Because this first limit that we showed with sine, we actually used it to show that this one is true. And so the limit as theta approaches 0 of sine theta over theta being equal to 1 was immediately helpful. Yeah, indeterminate on its own, but determinate with context. Yeah, and that's generally how like these indeterminate forms work. Hello, Ate. Can I help you? You've been fed already. Is it just time for pets? Let me see here. We have a guest. You're just showing the stream your butt. Come here. Turn around. Oh, you're done now? You don't care anymore? Well, whatever. I don't care anymore either. But yeah, so we can see why, like, having, you know, this, like, knowing what this limit is immediately useful, because the one that we showed for sine was immediately useful in showing the one for cosine. And so what we'll be able to do with these is like take limits involving like sine and cosine that are maybe otherwise indeterminate in the future and show that actually part of them, just like we showed up here, are actually like fit one of these forms that we've proven approach specific values. And so that's what we'll be able to do. And hey, what do you know? And so the limit as x approaches 0 of tangent of x over x, we can rewrite this as the limit as x approaches 0 of sine of x over x times 1 over cosine of x. And then we can say, since the limit of sine of x over x approaches 1, and as the limit of sine of x approaches, and the limit of 1 over cosine of x is equal to 1, then this will just be 1 times 1, which is 1. The 0th law of thermodynamics applies here as well. Well, that's why it's the law. Okay, here's kind of a funny one. We have sine of 4x over x. So my knee-jerk reaction in some cases like this would be used to like, or would be to use like the double angle formula to like rewrite this into like smaller and smaller multiples of like, instead of sine of 4x, get it down to sine of x. But we can actually just do this, where we can just rewrite this as the limit, like instead of the limit of sine of 4x over x, we can just rewrite this as 4 times the limit of sine of 4x over 4x. And then it doesn't matter that this is 4x because this is, and this is also 4x, because like all we need is for both angles to be the same for our original statement to be true. It doesn't matter that it's 4 times the angle or not. And so then here we can kind of show that the limit of this will just be 1, like before. And so this will just be 4 times 1. And so 4. The sign for x is no. But we like trig functions around here. Okay. Let's see. Should I go through these questions tonight, or should I save these for next time as a little bit of a review of what we covered this time? And so we can kind of review what we talked about this time by going over some of these limits. And then we can jump into limits at infinity and limits involving the difference quotient. You could call them differentiatives. Derivatives. Anyways. Solve for x and y by asking my x, why? I mean, that's, you know, we're all just trying to solve for why. Why is the ultimate question in life. You're back again. This is what she does. She just comes over here and rubs her head on the microphone. She's like resting her head on the microphone right now. I don't know if you guys will be able to hear her purr though. My microphone setup might be too good. Can we get you to purr? Can we hear it? Kind of funny how cats are covered in fur and still go to the warmest surface in the house. Yeah, I think it has to do with cats having like a higher metabolic rate or something like that. And so it's like they can use less energy on metabolism by staying warm or like going to a place where it's warm. Whereas if we're too hot, we actually like spend energy, you know, trying to cool off. I say, what do you want? You've been fed. Okay. Well, I think that's actually going to be where I'm going to end stream for today. I'm going to go figure out what Ate wants. Stop it. Stop. Go on. Stop rubbing on my microphone. You're messing up everything. And so I think I'm going to save going over these questions to be kind of like a nice review of what we covered today last time before kind of jumping into some of these other things. So like these one-sided limits and continuity and infinite limits before finally talking about, you know, our first big boss of calculus, the derivative. And so we'll jump into that next time. Is there anyone?
You do not save. You will not. Yes, but I love you.
You will not end. I'm going to end. That's it. I'm dying. I'm gonna end. Let's see. Who can we raid? You're watching Heretic? Is Heretic live right now? Oh, the movie Heretic. That makes sense. Thank you for your head patch, Pinky. I hope you have a good evening. Let's see. Well, that and me hungry. Well, I'm gonna raid the Astral Hammer. They're playing Satisfactory right now. And I love Satisfactory. And I also love the Astral Hammer. They're great. And so, join along on the raid if you want your free 250 channel points. Go say hi. And I hope you all have a lovely evening. Good night, everybody. Bye-bye.